very good. Yeah, so we're very pleased to have both Bernd and George to give a talk today. So Bernd will talk about the lanthanum 1111, I guess the string effect, right? Basically the pneumatic phase. And yeah, okay. So he's a director of IFW in Dresden. Okay, yeah, please. It's all yours.
So hello everybody. So first of all, I would thank the organizers for inviting me to give this presentation. I would like to bring you back to the early days of these iron-based superconductors by showing you some of our recent work on these 1111 type superconductors. Let me just show you an outline. So first, I would like to convince you that these systems are really extraordinary iron-based superconductors, and then I will show you some progress in crystal growth, and that's, I think, the main motivation for us also to pick up this story again. We're discussing pneumatic fluctuations in these systems. And then if I have time enough, I will also discuss some more recent work on strain-dependent measurements of Seeberg effect and Nernst effect, and which gives some additional information on the pneumatic instability and the connection to electronic structure of these systems. Let me first mention the people involved in this work, and the main person first was Rea Kappenberger. Maybe I first have to. She was the lady who managed to grow the nice crystals, or which I will show you later on. NMR and NQR measurements were done in Hayo and Piotr Lepucki mainly, and then the transport was done by Federico Caglieres and Xiaocheng Hong. And then I will also show you some thermodynamics done mainly by Federico Scaravacci. Good or bad metals? Well, let's take this as a starting point. So I think most of these iron-based superconductors, if you just look at the resistivity, behave like rather good metals. So this is an example from our own work. This is lithium iron arsenide, which has a small residual resistance, more or less T squared at low temperatures, and a large resistance ratio. But there is one exception, and this exception is indeed these 1111 type superconductors, and this the first report on superconductivity in these materials, and there you already see that you're basically dealing with something which is very close to localization, very close to insulating behavior. And the smallest resistivity which I found so far was one which was measured in a small single crystal here, and you still see, if you look at the absolute values, this is far away from being a nice metal. And you see here this typical phase transitions. You see above the phase transition, there's this increase, this tendency to localization. But the main message which you can take here from such a figure is that there is a strong decrease of the resistivity when you do this entering. And this immediately tells you that the scattering, which determines this very high value of the resistivity at high temperatures, that this scattering is intrinsic. It's not extrinsic. Or not only, mainly intrinsic. So you have a very strong intrinsic scattering, which is dominating the electronic transport, leading to the fact that these systems are very close to localization. And that's also what you see as a function of doping. This very early data where you see that when you leave this magnetic phase, you still have in the so-called underdoped region, still have this tendency to localization. Only if you go to very high doping concentrations, you end up with a resistivity which qualitatively looks like that, what we know from these very nice metallic systems. Okay, and this is, I think, is important because at the end of the day, these systems, these 1111 type systems showing the highest TC in the bulk iron-based superconductors, they are 50 or 60 Kelvin TC. So factor of 2 larger than that what you observe in all these metallic systems. Therefore, I think it's interesting to have a closer look on the materials, have a closer look what is determining really these very strange, unusual normal state properties which we have in these materials. Let me highlight another point. What's also quite characteristic for these 1111 type systems is something which people call poisoning effect of superconductivity. So you start from an optimally doped lanthanum 1111 type system, you plug in 0.2%, that's basically nothing, of manganese, and you destroy superconductivity. And it's not only superconductivity which you destroy, you can have a closer look on these publications. It's a normal state which drastically reacts on tiny amounts of disorder. Again, telling you that these systems are far away from being easy, simple, good metals. And this figure is also important because later on I will show you cobalt dope compounds, and this tells you already that this doping has a strong impact on the properties of these systems. Okay, so that's background. So the big step which we made in crystal growth was done a couple of years ago. It's a very unusual procedure, so-called solid state crystal growth procedure, which allows to grow pretty nice, well-faceted single crystals, three-dimensional single crystals. So that was first done on 1111 type crystals, so on the parent compound of these compounds, and it's still ongoing procedure. It's a very complicated process, and we still are not completely happy, and we are still improving this thing. But this shows the potential that you can really do single crystal studies, and which gives much more insight in the properties of these systems. Let's have a close look on the phase diagram, which is known also since more than 10 years, an old work by us. We have revisited this also for powder samples. What is known is that we have a very strong suppression of the magnetic ordering and the structure phase transition. And this is also seen in the more recent data. Now, meanwhile, we managed to get a smaller Tn down to 30 Kelvin. So it's not this first order-like behavior, at least not for the magnetism. There we can follow it down to lower temperatures. But there is still a clear separation between magnetic order and the structural phase transition. And so the pneumatic phase transition and magnetic ones are well separated. And what we still have is there is no coexistence between superconductivity and magnetism. So you have this well-separated region, and you end up with a region of so-called underdoped compounds where TC increases similar like we know it from some of the cuprates. So that's very similar to the first thing. We also managed to get, let's say, an internal standard. So the main problem is just to measure the electronic doping, and this you can do via NMR. And if you want to know more on that, you can have a look on this paper where we describe that. And you can even take all the literature data, put it on the same phase diagram, and then all the things fit together. So that's the phase diagram which we know for these compounds.
Bernd, do you mind if I interrupt you for a second?
No.
Maybe you'll talk about it, but near the doping where the magnetic order goes to zero, say when the chner is about 20 Kelvin or so.
Yeah.
Is there something unusual about the resistivity versus temperature, for example?
I cannot tell you about that. It's still, no, it looks like this close to localization behavior.
Okay, thank you.
I cannot tell you. In these cobalt dope compounds, which I discuss later on, this intrinsic scattering due to cobalt is so strong that I will not discuss that. But I will come back to that later.
Okay, thank you.
Okay. So that's the phase diagram we are dealing with for the fluorine dope compounds. So what we managed to do so far is crystals of a series of cobalt doped lanthanum oxygen. So lanthanum 1111. So cobalt doping means electron doping. This we know from the other systems, but it means also impurities. And I've shown you the figure of this manganese doping. That also means that we are not expecting the best crystals. We do not expect the best superconductors because we have intrinsically impurities in there, and they play a crucial role. But that's okay. That's a challenge for crystal growth, and the thing what we managed. And here we can do it up to rather high concentrations. We can really control the stoichiometry. Therefore, that was the first series of samples which we studied. And then we measured the phase diagram, and we did a broad spectrum of techniques to study that. And this is, let's say, a highest resolution measurement of the structure. So the dilatometry, where you see the temperature derivative of the lattice constants, you see the structural phase transition or the pneumatic phase transition here, and then you see the magnetic phase transition, even there, even the lattice constant, you can see that as a function of doping, the transition shifts to lower temperatures, as we know, and everything becomes very broad. So in particular, this structural phase transition becomes very broad if you start to dope it. And you can also see that from the lattice constants, which you can derive from such kind of measurements by measuring twinned and detwinned directions. And then you see this sharp transition becomes broader and shifts to lower temperatures before it disappears. You can also, of course, measure the magnetization just to follow the phase diagrams. So for the parent compounds, you clearly see these two phase transitions. And if you start to dope, the structure becomes very broad again. surprisingly, the magnetic transition becomes sharper, very nice visible. Some probably telling us something, but it at least gives you a chance to measure the phase diagram. If you go to higher doping, systems become reasonably good superconductors. Optimally doping, TC is small, but this is known because cobalt reduces TC, cobalt impurities reduces TC. But it's also clear that you see magnetism disappears at about 4.5%. Superconductivity is very strong with 6%, and in between we have, let's say, very weak superconductivity and no magnetic order. So we used also NMR to study the properties, and that confirms the things which you get from the macroscopic properties. So you see this very strong change of 1 over T1 when the magnetic order is still present, and then it disappears, and we lose the long range order. We can also, looking at the satellites, we can also determine there the structural phase transition. So at the end of the day, we end up with the following phase diagram, which shows again the splitting between pneumatic and magnetic phase transitions, shows decrease. We lose the signatures of the structural phase transition, pneumatic phase transitions at about 4%. We can follow the magnetism down to these concentrations, and then superconductivity emerge. So that's qualitatively very similar to this phase diagram. Maybe it's a little bit broadened here in this region, but of course we are now discussing compositions in the second digit of the cobalt. So that's the situation. So that's the phase diagram, and it's somehow similar to that what we know for the fluorine doping with a suppressed TC due to cobalt impurities. So now let's start. We have now single crystals at hand. Let's start to do more experiments. And the first thing what we can do, is well established meanwhile, is this pneumatic susceptibility measurements. So what we measure here is the strain derivative of the resistivity. So we piezo, we have crystals glued on top of that. We measure the strain, we measure the change of the resistivity, plot it as a function. So plot resistivity as a function of strain, take the derivative, we get the pneumatic susceptibility. This shows this divergence close to the structural phase transition. That's all well established for the other systems. Here you can see that this fit is not so bad. This Curie-Weiss fit is not so bad, and you can extract the Curie-Weiss temperature, which is close to whatever 130 Kelvin for the parent compound. And this you can do now for all these doping concentrations. So this Curie-Weiss fit is more or less working also for doped crystals. What you see then is that this Curie-Weiss temperature becomes smaller. And then you can follow this behavior up to very high concentrations. So this is now underdoped, and we go to overdoped samples. And when you just look at the Curie-Weiss temperatures, you see that it first is positive, and it crosses zero just to optimal doping. So this is the best superconductor which we have in these systems. And then it becomes negative for the overdoped compound. So it's very easy to see, easy to identify the optimal doping here from the normal state strain derivative of the resistivity. So this is the corresponding diagram of this pneumatic susceptibility, also this characteristic temperature, this Curie-Weiss temperature as a function of doping. You see the crossing here at 6%. It's just there where we have optimal doping. So in some sense, you continue this line here, though the structure phase transition or the real 3D order disappears. Just looking at the characteristic energy scale, we follow this line, and it hits exactly the zero for optimal doping. Or you can also, yeah.
I'm sorry. Can I ask a question?
Yeah.
Right. So in the parent phase, you observe T pneumatic about 20 or 30 Kelvin below the actual transition, right?
Yeah.
But it looks like from this phase diagram that they actually are about the same temperature when they reach the quantum critical point. No?
That's correct. Yeah, I can. So you see, here's 130 degrees is TM. The structural phase transition is 150 degrees. So, but if you go to this TNM at higher doping, it enters the zero.
Okay, so in some sense, the separation temperature gets smaller and smaller as you're approaching the
separation temperature between, let's say, the ordering temperature and this TNM becomes smaller, and then of course I've shown you the data. This transition becomes extremely broad, and therefore I don't know what that means. Yeah. But
thank you.
not only look at the pneumatic transition temperature, we can also look at these, let's say, susceptibility. So what I've plotted here is just the absolute value of these strain derivative. And you just look at the data, it's raw data, nothing is done with that. So it's the optimal doping, so we have a pretty large number here. So there's a very strong change of the resistivity as a function of a strain. If you go to overdoping, it becomes much smaller. And if you go to underdoping, it also becomes much smaller. It also becomes smaller when you go to the parent compounds or to these strongly overdoped compounds. So without any manipulation of data, you just take the raw data and plot that as a function of doping, you end up with this diagram. And then you see this, what I would call a double dome feature here for these pneumatic susceptibility. And it's easy. So one, of course, this is, let's say, mimicking our superconducting dome. There's nothing, just taking the resistivity, the strain derivative of the resistivity, we directly can see the region where superconductivity occurs with a maximum at least 6%. And the other thing here, which we see here, is also a special point in the phase diagram, is exactly the phase diagram, well, close to the region where magnetism disappears. And it's, of course, let's say, natural to assume that here, this is the coupling between pneumatic fluctuations and spin susceptibility, which we see there. And that there is a coupling, we know, of course. We know, for example, from measurements of NMR, when you go to the magnetic phase, to the pneumatic phase transition, you see a strong enhancement of 1 over T1T, so strong slowing down of spin fluctuations. So there is certainly a coupling between pneumaticity and spin fluctuations. And of course, if you have this magnetic transitions becoming, let's say, very unstable, if you enter close to the quantum critical point of the spin susceptibility, enhancement of spin susceptibility, you can also expect something going on in the pneumatic fluctuations. And that's what I think what's going on here. And of course, this means that we have a very interesting region here. So we have these very slow pneumatic fluctuations, which are coupled to the spins. And somehow this should also show up in unusual spin behavior. And that's also what we see. So what I've plotted here is also measured on these single crystals now, the NMR relaxation rate on compounds where you still have the magnetic order. You see the strong peak. And then this magnetic order disappears. And then you observe a very funny, very unusual behavior of 1 over T1T. That's plotted here for one of these underdoped compounds, which is hardly not really superconducting. And that's just a comparison of a compound which still shows magnetic order. We have this strong enhancement, this strong peak, which you expect at the magnetic ordering. And then we have this very funny, very unusual behavior of 1 over T1T. And this is still present in the optimally doped compounds. So the compounds shows the highest TC. Also there, we have this very unusual behavior of 1 over T1, telling you that at least this whole underdoped region is a very unusual material. So we have this very soft pneumatic fluctuations, very soft lattice, very soft orbital degree of freedom, and you have an extremely soft spin degree of freedom. And all of that is strongly coupled to electron transport. And therefore, it's apparent that you have this extremely strong scattering of the electrons. And this, of course, explains you, at least qualitatively, that you are very close to localization. And only if you go to very high doping, these things disappear and things more and more become like usual metals. Okay, these similar things you can also observe in these fluorine doped compounds. This we did earlier already, that you also have this very funny relaxation with very funny, very unusual slow spin fluctuations. And I think now it's becoming clear that this is definitely connected also to these pneumatic fluctuations, which are very soft in these optimally doped compounds. And only if you go to overdoped compounds, you end up with something which looks more or less like a usual metal. Okay, that is the first part. Maybe I add a couple of transparencies on these thermoelectric properties, which give you even more information now that these systems are really very unusual metals. So what we are measuring now is we take again such a piezo stack. We take a sample, we measure we apply a temperature gradient, and we measure the thermal power and the Nernst effect. And both of that now as a function of a strain. And the strain which we can apply here is tiny, 0.08%, but it's still sufficient to see a signal. And that's shown here, just an example. So that's the way how we do these measurements. So we switch on a heater. The heater induces Seebeck, the thermal power. So you see a voltage. Then we switch on the piezo and you see a change of the Seebeck effect, switch off the piezo again and the heater. So that's then the strain dependence of the Seebeck effect. And that's here measured at a different temperature. And you see the Seebeck effect is negative and the strain effect is still positive. So you can really discriminate these two things. What we then do is measuring these effects, these small effects, as a function of strain plotted in this way from the slope. We get then the change of the Seebeck effect as a function of strain. And the same you can even do for the Nernst effect, which is even a little bit more complicated because now you have to apply also magnetic fields, negative and positive ones, and you have to subtract the things. But also here, you can easily follow the change of the Nernst effect as a function of the strain. That's by itself is already a real surprise because typically these effects are zero in usual metals, and now you can even measure their change as a function of these tiny strains. Seebeck effect, what do we measure here? So it's not scattering. So it's really a different quantity than the resistivity. What you measure here, if you, for example, take this easy mod formulas, what you measure here is the energy derivative of the conductivity. So energy derivatives of density and mobility. And it's, of course, well known that it's very, very sensitive to details of the Fermi surface, Seebeck effect. So and if you have the parent compound equal to 0, so you have basically undoped compounds, so holes and electrons with the same amount. Therefore, you have this crossing of the sign close to 0. If you electron dope the system, it becomes negative. So in both cases, we can then now follow the strain dependence of these things. And the first message is it does not change when you change the sign of the Seebeck effect. So that simply means that the strain derivative is independent on the sign of S. And this, the easiest way to explain this is that this really band selectivity of pneumatic fluctuations. So apparently, only part of the Fermi surface, if you have these holes and electrons, really feels pneumatic fluctuations. Next thing is that in both cases, you can again fit these Curie-Weiss laws, and the Curie-Weiss constants which you obtain here are very similar to that what you get from the resistivity. However, these X dependence of the size of the effect is different. So the Seebeck effect here is much larger in the parent compound than it is in the dope compound. So in that sense, already telling you that it's not easy to take the same susceptibility. It's not straight to take the same susceptibility. And it's also maybe remarkable that when you do the same experiments on the barium 1-2, it's surprisingly similar. So that seems to be rather generic, this behavior, how this detail of the Fermi surface changes as a function of strain. Nernst effect is even more complicated in some sense because in simple metals, the Nernst effect is always 0. And some of you might remember all the discussions on the cuprates on the reason of the Nernst effect, which I will not solve. So Nernst effect is the energy derivative of the hole mobility. And here you see compounds, the parent compound and the dope compound, very much different in the ordered phases, but at high temperatures rather similar. And also for the Nernst effect, we can follow this change as a function of a strain, which is, for me, it was a real surprise. That really tells us that really details of this Fermi surface are extremely strongly dependent on details of the lattice. You can determine these susceptibilities if you want, a Nernst susceptibility, Curie-Weiss constants as you see it from the resistivity. That's easy. Again, finding for parent compound is larger than that for the dope compounds. And let me at least show you some first attempt how we can discuss these things. So when you write down the Seebeck effect, is take this mod formula. You can discriminate, or you can write it up in the following form. It's a product of so-called Peltier tensor times the resistivity. And here I assume a single band, so I forgot about all these complications due to multi-band effects. And if you do that, you can, and this may be relevant for this doped compound, you can determine a Seebeck susceptibility, which then is a sum of a susceptibility coming from this Peltier tensor. And this is something which is really measuring details of the Fermi surface usually, plus the second contribution, which comes from the resistivity here. And this is the susceptibility from the resistivity, which we know, which I've shown you earlier. And you can do this analysis, and then you find out that you definitely need two kinds of susceptibilities. You cannot take the resistivity values to explain the Seebeck effect. That's also already clear from the concentration dependence, and both of that have similar sign. So there's certainly a very strong change of the Fermi surface. It's quite natural to assume that this is really due to some orbital degrees of freedom, and that might be a starting point for let's say, more calculations. What we did then is to take these susceptibilities, which we derived experimentally, to model the Nernst effect. This can do that along these lines, and details are described in this paper. And this is, again, without any assumption, without any fitting parameter, you can reproduce the Nernst data then from thermal power and resistivity and from their strain derivatives. That by itself is already a funny story, a very unusual thing, but telling us that this approach, having these two kind of susceptibilities, two kind of strain dependence, makes a lot of sense. Okay, that's what I wanted to tell you today. So I've presented you some, let's say, first results on these first series of single crystals. It's still work in progress. We try to get the fluorine doping working. We have now also systems with higher TC. I've shown you this kind of phase diagram. I've shown you this very prominent, very pronounced double peak feature, which you see here in the pneumatic susceptibility, somehow inferring that indeed pneumatic susceptibility is strongly coupled to superconductivity here, and it is coupled to spin fluctuations, which leads to very strange behavior in the normal state of these materials. And then at the end, I've shown you some first results on strain derivatives of more complex transport properties like Seebeck effect and Nernst effect. All of them strongly depends on lattice, very strongly shows that the pneumatic instability is very crucial for the electronic state here. And I think that also gives us, let's say, first new approaches to understand this coupling, which seems to be band selective, and which seems to be very strongly connected to the Fermi surface. So thank you very much for your attention. And if you want to learn more on that, there are papers on all these different things which I discussed today. In particular, this strain derivative of thermoelectric effect will appear soon in this Quantum Materials journal. The resistivity has been published last year in PRL. So thank you very much.
Thank you very much, Bernd. Yeah, any questions? Yeah, this is a very nice talk. Hey, Jan.
Hi, guys. How do
Hey,
you
how are
like?
you? Good to see you. Hey, Jan.
Yeah. It's not only to show my hair. I mean, you have a lockdown of barbershops, so I haven't been getting a haircut for the last 2 months. Next week I'm up. Yeah, I haven't been paying too much attention to these iron superconductors for a while, but when I was listening to Bernd in the first half, I got kind of a very simple thought. Right, so you look at the pneumatic susceptibility, and it's basically associated with electron system, right? You look at the resistivity, and then you have this trouble that you look at the structural phase transition, right? That starts to broaden out. But it seems that the pneumatic susceptibility is still behaving in a pretty orderly manner, right? It's a nice QE wise, etc. Now, this may be an obvious thing, and I don't know whether everybody realizes it, but I would rationalize this as the electron system wants to do the pneumatic transition, right? So pneumatic popper, and when the pneumatic susceptibility gets large enough, the lattice couples in and promotes the transition to a first order, while by itself it would be like to be a second order, right? It's Curie-Weiss. And then when you have the first order transition and the lattice is coupled in, the lattice is talking in a very different way with this order than the electron system is doing. Right? The electrons are kind of self-annealing things. Right, so could it be that this sort of disconnect between the neat and orderly behavior of the pneumatic susceptibility contrasted with this very disorderly behavior of the orthorhombic transition is just about it, this sort of, turning into a first order transition when the lattice starts to feel the pneumatic susceptibility. And then when you have that, you can have this sort of Imri-Ma type of physics, right? The first order transition plus disorder gives you puddling that is smearing out a transition. Could that be? Is this a thought that other people have had?
I don't know whether I really got your point correctly, but definitely I think there's something interesting and correct in there, because we have this extremely strong pneumatic susceptibility here at low temperatures. And why is there no long range order? What's really inhibiting this long range order here? And I think that could well be disorder, but not disorder in the sense of, let's say, some impurity atoms. I've shown you this in the beginning.
I'm saying something else, right? So there's this ongoing discussion forever whether this pneumaticity is driven by the lattice, right? So that you just have a silly structural transition, or is it like the electron system by itself wants to form a kind of quantum-liquid crystal or liquid crystal, and therefore you get this very strong pneumatic susceptibility that you see in the resistivity, which is an attitude of electrons, right? You really look at the size of the electron system. And they're kind of coupled always, right? So when there's pneumatic susceptibility, which is purely electronic, starts to grow, at some point, there will be kind of a critical temperature where the lattice starts to communicate with it. And then, it's not very surprising to find that it turns into, as I remember it, a first order structural transition from tetragonal to orthorhombic. Having said that, when you have the lattice and there is disorder, right? You do expect that you get a sort of puddling, which is just silly, having kind of orthorhombic domains that are messy in a tetragonal background, blah, 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 blah. Right, so where you could switch off the electrophonic coupling, it could be that you would have a very neat second order electronic pneumatic transition. But it's in fact obscured because you see it indirectly through the lattice, and the lattice feels a lot more about its disorder than the electron system is doing. The electrons are self-averaging, right? They're self-annealing, they're very quantum mechanical, they're way more liquid than atoms are, so to say. Could that be?
First of all, these systems do not show first order transition. So they're already second order in the parent compound. First order is, I think, in barium 1 to 2, in these compounds is second order. But I think they're, but I agree. Yeah, it's
first order. Tetragonal to orthorhombic structural transition.
The second order, at least if you believe our thermal expansion and thermodynamic properties. But nevertheless, you're right. I think it is basically an electronic instability, which we probe via these strain dependencies. Yes, yeah. It's electronic instability and also this surprising similarity. And I did not show you everything. I showed you only, let's say, the strain derivative of the Seebeck effect, which is identical for barium 1 to 2 and for these systems. You can have a look at the Nernst effect. It's identical. You have this completely different system, structurally completely different, a lot of different properties, scattering completely different. One is a nice metal, the other is a lousy metal close to localization. Nevertheless, these very sensitive probes of the Fermi surface, so thermal power typically measures if you have a peak in the density of states or something like that. These are basically identical in these systems, telling you that this instability itself and also somehow the strain derivative, which is somehow still a little bit of coupling to the lattice, is very, very similar. So I'm absolutely sure that at the end of the day, this is an instability of the electronic system. Of course, lattice picks it up. And then this thing of disorder, which you mentioned, I think that's very, very important, in particular to understand this funny phase diagram where we lose somehow our structural phase transition. Also, it becomes, so here it's fairly sharp, it's a very nice phase transition, and then you start to dope and it becomes broader and broader. In the same samples, The other transition is sharp and sharp, becomes sharper and sharper. So it's not some sample property. It's something which is more intrinsic. And in some sense, the answer, I think one possible answer of that is given by this figure here. And that's the doping dependence, that as function of doping, we induce some additional sites here. We induce some kind of disorder in this system. And that's characteristic for these 1111 type compounds. But that's another talk. So yes, it's an electronic instability. Yes, lattice picks it up. And the lattice, the long-range lattice order is much more sensitive to an intrinsic kind of disorder, which you have in there. And finally, we end up with an electronic instability only. You still see this very nice boost of the pneumatic susceptibility, but without a long-range order of the structure.
I should keep my mouth shut, but that's basically what I'm saying, right? That the lattice may be much more sensitive to the disorder than the electron system is. In this sense, you see.
And that's what we see here. Maybe you lose the structure phase transition, but you can still, if you measure the susceptibility, you still can follow the electronic response, which just hits this line.
So maybe
can I maybe continue along the same line, more or less? I also wanted to ask myself, hi Ben, as to all these iron-based superconductors, people always speak about pneumatic, but usually people have in mind completely different microscopic mechanism. It might be simply any structural type of transition, or it might be something connected with orbitals, or with Fermi surface, or maybe with biquadratic exchange, purely magnetically driven, and so on. And my question is actually from your data. Can you say something about anything, actually, about possible microscopic origin underlying all these phenomena?
Okay, probably. So if I would say, okay, already the fact that somehow this magnetism and the other transition changes in a different way, once disappears previously, the other later on, might indicate that it's not, let's say, the same instability which you see here, which drives the system to the spin density wave or to the magnetic state, and the other one drives this pneumatic instability. But of course, a lot of theoreticians will disagree. They say, okay, that's
fluctuations.
Which I don't know. So that's what I can say. What I can, maybe we have to go a little bit further in analysis of this thermotransport, because there it's not scattering. And I think typically when people discuss pneumatic susceptibility, usually they take this anisotropic scattering as a main mechanism. And I think what we see here is that there is indeed a very subtle response of the Fermi surface as a function of strain. And I think this, for me, looks more like orbitals. That's one story. Then the other story, which is also, let's say, maybe is something which is homework for theoreticians. So why is, does this behavior here, so we have the sign change of the thermal power, but the pneumatic susceptibility shows the same sign. So it's really, let's say, orbital selective. It's really related to one part of the Fermi surface only. And this, again, could give us, let's say, at least then if we do some more realistic modeling of this, this could give us an idea how really the intrinsic mechanism of these things comes up. So
but at least it looks that it's not spin driven, yeah?
I would say that this looks more like orbital driven, yes.
So so let's quickly get two more questions. Chimel and then Luca. Yeah.
Yeah, Bernd, so I had this question about 1111 versus 122. You know, as you mentioned at the beginning of the field, the evolution looked very different, and now you're telling us that maybe there's a more similarity than realized earlier, which is wonderful. I had two questions in this regard. So in nickel-doped 122, and I think in cobalt-doped 122 as well, there was some indication for glassy behavior in the near optimal doping at low temperatures that sort of interrupts the higher temperature quantum critical like behavior. And I wonder whether in this system you have the way to measure slow response or just dynamics in some way. That's question number one.
So let me first maybe first a short remark to the similarities and differences between 122 and 1111. So what remains is this remarkable difference in the normal state that we really have this system which is close to an insulating state. So if you look at the resistivity, it's really different. So the coupling is much stronger here. I don't think that this is really understood. What is definitely the case, we have a more two-dimensional systems. We have not this intermetallic behavior, not 3D systems. We have this oxygen in there. Maybe the lattice coupling is stronger. I don't know, but this remains. Now, if you already go to something like thermal power and Nernst effect, the similarity is unbelievable. Even such a quantity like the Nernst effect as a function of doping is basically identical, telling us that these details of the Fermi surface have to be very, very similar in these 1111 type compounds. Okay, that's maybe the point to point one. Coupling is somehow stronger, TC is higher, resistivity is much higher. Okay, maybe that's not so stupid, but that's what we learned. What the underlying electronic structure, details of it seem to be very, very similar in 1 to 2 and 1111 compounds. Okay, now the glassy behavior. Of course, we have the NMR, and for the NMR, this I did not push that a lot. So we have this. Okay, let me have where it was. Yeah. So you have these long range order things, but they're on top. There's of course some kind of short range order phenomena going on there. It's a little bit glassy, at least short range ordering. Let's call it like that. And that's maybe it's connected or is appearing close to this, let's say, quantum critical point for magnetism. On the other hand, this is really challenging to get the crystals. And this, I think it's too early. For me, it's too early to say this is crystal or this is intrinsic. This I don't know. But there is, from the NMR, we have some, also, if you look in the paper, which is on the archive, you see there is a region in the phase diagram where we see some kind of short range phenomena going on.
It's
Is
very
it commensurate or incommensurate?
Or an NMR probably doesn't know.
I have no idea. So at the moment we have these NMR data yet. So there's, as far as I know, at least for our crystals, there's no neutron data yet.
Just to follow up, so in 1 to 2 again, one could maybe avoid this glassy-like behavior by looking at the phosphorus doping as opposed to be cobalt or nickel doping. And I was wondering whether, from materials perspective, whether one could also look at 1111 phosphorus doping.
Yes, of course. The big challenge is to get fluorine doping in there, because fluorine is out of plane doping. And just looking at resistivity, looking at the phase diagram, there's tremendous. So the TC in this cobalt, the maximum TC which you get in the cobalt doped samples is about 11 Kelvin. If you take the same samples with fluorine doping, you get 30 Kelvin. And these systems are much cleaner. But it's even more challenging to get these crystals, and we are working on that since years, I would say. And so far, we are not able to get, let's say, the phase diagram for the single crystals or fluorine doped crystals in a way that I can present it. Maybe I can do it next year, but at the moment, I'm not able to do that. Yes, there is a way. It's fluorine doping. It's out of plane doping, which should be. If crystals are nice, which should be really perfect in that sense.
Yeah, Luca?
Just a comment, but that you are doping with fluorine or cobalt, you get the disappearance at the same doping. So
more or less.
So and the two.
You see, for fluorine doping, the phase of, at least as far as we know, is more sharp. So this, and it is maybe slightly smaller concentrations, about 3%. For cobalt doping, it's 4%, but it's nearby. And now we are discussing real samples where 3% of fluorine doping and 4% of cobalt doping. That's okay, the precision of measurements. I think could be that for fluorine doping it's slightly smaller, that doping is slightly more efficient, but the difference is pretty small.
Okay. So if no further question, let's thank Bernd again.
Okay. Thank you very much.
Yeah, thank you very much. Yeah.